Welcome back to another deep dive here on AI.Code.Cast. Today we're going to be cracking the code of letter combinations of a phone number.
Oh, wow. That sounds pretty intriguing. Like something we do all the time without even really thinking about it.
Yeah, exactly. Like every time you type in a number on your phone and it magically suggests words, like that's the problem we're going to be diving into today.
So basically, we're trying to figure out how to generate all the possible letter combinations from a given sequence of digits, just like a phone's T9 system.
Yeah, you got it.
Yeah.
So say you type in 23, our goal is to have the program spit out, ARI, AF, and all those other different possibilities.
Okay, I see the challenge here. But where do we even begin with something like this?
Well, before we jump into solutions, let's lay down some groundwork. The problem statement has this really cool constraint that the input number string won't be longer than 4 digits. Why do you think that's important?
Hmm, that's interesting. I'm guessing it might have something to do with the computational complexity. Maybe it simplifies things because we're dealing with a smaller set of possibilities.
You're on the right track.
Yeah.
That constraint is a big deal because it allows us to use a brute force approach.
Brute force? You mean just trying every single combination?
Exactly. If we had a massive input string, brute force would take forever. But since we're limited to just 4 digits, we can actually generate every single letter combination without, making our computers sweat too much.
That makes sense. So brute force is our starting point. Now, how do we systematically generate these combinations? What's the logic behind it?
There are actually a couple of really clever approaches that we can take. The first one that comes to mind is backtracking.
Backtracking, does that mean like hitting the backspace key on our keyboard if we mess up?
It's kind of like that. Imagine you're navigating a maze. If you hit a dead end, you backtrack to the last decision point and you try a different path. Yeah. In this case, each path represents a potential letter combination.
Okay, so we're essentially exploring different combinations until we hit the jackpot. Can you walk me through an example? Let's say our input is 23 again.
Sure. Let's say we start with A from the digit 2. Then we explore all the possibilities for the next digit 3. That would be D, E, and F. So we get add A, E, and F.
Got it. We've exhausted the options for A. What happens next? Do we just move on to B?
That's where the backtracking magic comes in.
Yeah.
We go back to 2, pick B, and repeat the process with 3, again trying BD, BBF, and so on.
So we're systematically exploring all the letter options for each digit and then backtracking to try a different path if we've explored all the possibilities for a particular digit. It's like a really methodical search.
Precisely. Now, I'm curious about something. Remember how we talked about the efficiency of brute force being okay because of the 4-digit limit?
Sure.
How would we express the efficiency of this backtracking solution in a more formal way? Have you heard of Big O notation?
Yeah, big O notation rings a bell. It's about how the runtime of an algorithm scales with the input size.
Right. Exactly. And for this backtracking solution, the efficiency is O4, where N is the number of digits.
Hold on. Oh, foreign. For our listeners who might not be familiar with Big O, what does that actually mean in plain English?
It basically means that the time it takes to run this algorithm grows exponentially with the number of digits. Think of it like this. If you have a small party, ordering pizzas one by one is fine. But if you're hosting a huge event, you need a more efficient system, like bulk ordering. Big O helps us understand how the time it takes to solve a problem grows as the input gets bigger.
That's a great analogy. So even though the time grows exponentially because our input is capped at 4 digits, it's still manageable, right?
Right. Well, what if we wanted to visualize how backtracking works? It feels a bit abstract just talking about it. What image comes to mind?
For me, it's like a tree. Each level of the tree represents a digit from our input, and the branches at each level represent the possible letters. We're essentially traversing this tree, exploring each path until we reach the end, which represents a complete combination.
I love that. That makes the process much clearer. But backtracking isn't the only way to solve this problem. There's another approach that uses iteration. Do you want to take a stab at explaining that?
Sure. With iteration, instead of recursion and a tree structure, we think of building a list of combinations step by step, like constructing a wall brick by brick. We start with an empty list, and then for each digit, we expand the list by appending each possible letter to existing combinations.
That's a great explanation. Could you walk us through an example using 23 again so our listeners can see how it works?
Absolutely. We begin with an empty list, then for the digit 2, we'll have A, B, C. Then for each of those, we add D, E, F, resulting in add A, E, F, B, D, B, B, F, C, D, C, C, F.
Perfect. Now I'm curious, how would you describe the efficiency of this iterative approach in terms of Big O notation?
Well, it turns out the iterative approach also has a time complexity of O4n, just like the backtracking solution.
So both methods have the same Big O complexity. But do you think there might be any practical differences in terms of performance?
That's a great question. While the big O notation is the same, the iterative approach might be slightly more efficient in practice because it avoids the overhead associated with recursive function calls. It's like taking the express train instead of making multiple stops along the way.
That makes a lot of sense. It's fascinating how different approaches can have the same theoretical complexity, but still have subtle performance differences in real-world scenarios.
Exactly. Choosing the right approach often depends on the specific context and the trade-offs you're willing to make.
So we've got two solid approaches, backtracking and iteration, and both can crack this letter combinations of a phone number code. But before we declare victory, I think it's important to address some common pitfalls that people might stumble upon when implementing these solutions. What are your thoughts?
Absolutely. Understanding these potential pitfalls can save a lot of headaches down the road.
Let's start with backtracking. What are some things people might trip over when trying to implement this approach?
One common mistake is forgetting to backtrack properly after exploring a particular path. It's like getting so focused on one route in the maze that you forget to turn back and explore other options.
Right, and I imagine that could lead to missing some valid combinations.
Exactly. If you don't correctly backtrack by removing the last added letter after exploring its combinations, you'll end up with incorrect or incomplete results.
Okay, so backtracking needs careful attention to detail. What about the iterative approach? Any potential traps there?
With iteration, one thing to be mindful of is how you build the list of combinations. It's important to make sure you're adding new letters to existing combinations correctly and that you're not accidentally modifying the original combinations while iterating. It's like building that wall. You need to make sure each brick is placed correctly to avoid a wonky structure.
That's a great way to put it. Speaking of things that can make your code wonky, we can't forget about edge cases.
Edge cases. You mean those pesky scenarios that try to break our code?
You got it. They're like the unexpected detours on our coding journey. And one important edge case here is an empty input string.
Ah, that's a good one. If someone enters an empty string, what should our program do?
Well, we can't really generate any letter combinations from nothing, right?
Right.
So our code needs to gracefully handle that situation and return an empty list of combinations.
Right. It's all about making our code robust and able to handle anything that's thrown at it. We need to think like testers and try to break our own code before someone else does.
Exactly. Thinking about those edge cases can sometimes reveal hidden bugs or logic errors that we might have missed otherwise. So it's always a good idea to be prepared. And I think we've covered a lot of ground in this first part of our deep dive.
We definitely have. We've explored the problem, discussed the power of brute force, and delved into two clever approaches, backtracking and iteration. We've even talked about visualizations and potential pitfalls to watch out for.
I'm feeling pretty confident that our listeners are starting to grasp the essence of this letter combinations of a phone number challenge.
Me too.
Hmm.
But we're not done yet. In the next part, I think we should dive deeper into pseudocode for each approach, giving our listeners a more concrete sense of how to implement these solutions step by step.
Sounds like a plan. Stay tuned, everyone. The journey continues in part 2, where we'll transform these concepts into actionable steps.
Welcome back to AI.Code.Cast. In the last part, we set the stage for tackling the letter combinations of a phone number problem, and we explored two powerful approaches, backtracking and iteration.
Yeah, and now it's time to roll up our sleeves and get down to the nitty-gritty of how to actually implement these solutions.
I'm excited to dive into the code.
Me too.
Yeah.
But before we get lost in the, syntax and all that, let's start with pseudocode.
Oh, that's a great idea. Pseudocode. It's like a blueprint that outlines the logic without getting bogged down by specific programming languages.
Exactly. So it helps us focus on the core concepts and makes the implementation process much smoother. Shall we start with the backtracking approach?
Absolutely. Let's break down how we would structure the pseudocode for backtracking. Remember, it's all about exploring those paths like we're in a maze.
Okay, so first things first, we need a way to map each digit to its corresponding letters. Right? That's our trusty guide in this maze.
Right. It's like having a map that tells us which paths are available at each junction.
Exactly. We can use a simple structure like a dictionary or a hash map, where the keys are the digits and the values are the lists of letters.
Got it. So for example, the key 2 would have the value, ABC3 would have DEF, and so on. Now that we have our map, how do we actually implement the backtracking logic?
This is where the recursion comes in.
Yeah.
Let's define a function. Let's call it backtrack.
Yeah.
This function will be the heart of our backtracking solution.
Okay. What parameters should this backtrack function take?
It needs a few key pieces of information. First, it needs the current combination we're building, which starts as an empty string. Think of it like the path we've taken so far in the maze.
Makes sense. What else?
We also need to keep track of the index of the digit we're currently processing. This tells us our current position in the input digit string.
Right, like knowing which junction we're at in the maze? Anything else?
And finally, we need the input digit string itself, which represents the entire maze, and a list to store all the complete combinations we find. Think of it like a treasure chest to store all the successful paths we discover.
Perfect. So we have our map, our backtrack function, and its parameters. Walk me through what happens inside this function.
Right, so inside the backtrack function, the first thing we do is check if we've reached the end of our input string. That means our index is equal to the length of the digit string.
So if we're at the end of the string, it means we've formed a complete combination, right?
Exactly. We found a successful path through the maze. So we add this complete combination to our list of results, our treasure chest.
Okay, that's the base case. What if we're not at the end of the string yet? What does the algorithm do?
Well, if we're not at the end, it means we're at a junction in the maze and need to explore different paths. So we grab the current digit from the input string based on our index.
And then we use our handy map to get the corresponding letters for that digit, right?
You got it. Now, for each of those letters, we add it to our current combination string. It's like taking a step down a particular path in the maze.
Okay, we've taken a step. What happens next?
Now the recursion kicks in. We call the backtrack function again, but this time with the updated combination string and the index incremented by 1.
Ah, so we're essentially moving to the next junction in the maze and exploring all the paths from there, right?
Exactly. And this recursive call will continue until we hit the base case where we've reached the end of the input string and found a complete combination.
I'm starting to see the beauty of recursion here. It elegantly handles the exploration of all these different paths.
It really does. But remember, we need to backtrack after exploring all the possibilities for a particular letter. It's like turning back at a dead end in the maze and retracing our steps to try a different path.
Right. So after making that recursive call, we need to remove the letter we just added from the combination string. That brings us back to the previous junction, ready to explore other paths.
Exactly. This backtracking step is crucial to ensure we don't miss any possible combinations.
This has been a great walkthrough of the backtracking approach. I think our listeners now have a solid understanding of how the logic works. But what about the iterative approach? How would we structure the pseudocode for that?
For the iterative approach, imagine we're building a wall brick by brick.
Okay.
We'll start with a list containing an empty combination, and then for each digit in the input, we'll expand our list by adding each possible letter to the existing combinations.
Okay, that sounds straightforward enough. Can we walk through an example using our trusty 23 input?
Sure. Initially, our list would just have an empty string. Then looking at digit 2, we add each of its corresponding letters, A, B, C, to the existing combination, which is just an empty string at this point, resulting in ABC.
So we've essentially expanded our initial empty combination into 3 new combinations. What happens next?
Now we move to digit 3. For each combination in our list, A, B, and C, we add each of the letters corresponding to 3, D, E, F. So A becomes add, A, E, F, B becomes B, D, B, B, F, and so on.
Ah, so we're iteratively building up the list of combinations. In the end, we'll have all 9 possible combinations.
Exactly. It's a systematic process of appending letters based on the digits in the input.
The pseudocode walkthrough for both backtracking and iteration has been super helpful. I think our listeners are now well equipped to translate these concepts into real code. But before we wrap up this part, do you think there's anything else we should highlight about implementing these solutions?
You know, one thing that comes to mind is the importance of testing your code thoroughly.
Testing, absolutely. It's a critical step that many new coders might overlook.
Exactly. Writing tests helps us ensure that our code behaves correctly and handles different inputs as expected, including those tricky edge cases we discussed earlier.
Right. We don't want our code to crumble when faced with an unexpected input. Testing helps us build confidence in our solutions.
So in addition to the pseudocode, I encourage our listeners to think about how they would write tests to validate their implementations. It's a valuable skill that will make them better coders in the long run.
Couldn't agree more. And remember, folks, there's often more than one way to solve a problem. Don't be afraid to experiment, explore different approaches, and find what works best for you.
Well said. It's all about learning, growing, and expanding our coding toolbox. And with that, let's take a short break. When we come back, we'll wrap up our deep dive by discussing some key takeaways and leaving you with a challenge to ponder. Stay tuned. Welcome back to AI.Code.Cast, We've journeyed through the letter combinations of a phone number problem. We've explored backtracking and iteration. We even crafted some pseudocode blueprints.
Yeah, it's been quite the adventure, hasn't it? We traversed mazes, we built walls, we even gathered some treasure along the way.
We sure have. But before we hang up our coding hats, let's take a step back and reflect on what we've learned.
Yeah, what are the key takeaways that you think our listeners should walk away with?
Well, first and foremost, I think this problem really highlights the power of constraints. Remember how that 4-digit limit allowed us to use brute force?
Right. That seemingly simple constraint made a world of difference in our solution approach. It's a great reminder that understanding the problem's limitations can often simplify things.
Absolutely. And speaking of different approaches, we saw how both backtracking and iteration could crack this code.
Yeah, it's fascinating how two completely different algorithms can lead to the same result. Like backtracking with its elegant recursion, like navigating a complex maze, and then iteration with its methodical step-by-step approach, like building a sturdy wall.
Exactly. And I think the visualizations we discussed really helped bring those concepts to life. The tree structure for backtracking and the brick-by-brick analogy for iteration like those just painted a vivid picture in my mind.
Yeah. Visualizing algorithms can be incredibly powerful for understanding how they work. It's like having a mental map that guides you through the logic.
And let's not forget the importance of pseudocode. It helped us break down the solutions into manageable steps without getting lost in the syntax of a specific programming language.
Yeah, pseudocode is like sketching out the blueprint before you start building, you know? It helps you clarify your thoughts and makes the actual coding process much smoother.
We also touched on common pitfalls and the importance of testing. It's easy to get caught up in the excitement of coding and kind of forget about these crucial aspects.
But testing and anticipating potential errors are what separate good code from great code.
Well said. It's all about being thorough, thoughtful, and always striving for those robust solutions.
Now, before we sign off, I'd love to leave our listeners with a little challenge. Remember that constraint we talked about, the 4-digit limit? What if we
Right.
remove that constraint?
Oh, that's interesting. Things would definitely get more complex. We couldn't rely on brute force anymore, right?
Exactly. It would be like navigating a maze with infinite paths. We would need to think about more efficient algorithms and data structures to handle larger inputs.
That's a great challenge for our listeners to ponder. How would you modify the solutions we discussed to handle much larger inputs? It's all about, pushing the boundaries of your coding skills and exploring new possibilities.
And remember, there's no one right answer. The beauty of coding lies in the creativity and problem-solving skills that you bring to the table.
Well, folks, that brings us to the end of our deep dive into letter combinations of a phone number. We hope you've enjoyed the journey and feel empowered to tackle this problem and many others like it.
Until next time, happy coding.